So we have solved the Schrodinger equation for hydrogen atom in the last few videos, right? And we had a pretty lengthy solution for the Schrodinger equation for the hydrogen atom. It was very adventurous, perhaps, but we finally got very good solutions, right? So in that respect, we all are happy. And during the solution of the Schrodinger equation for the hydrogen atom, we encountered certain numbers. Okay, these are n, l, and m, right? These are the numbers we became familiar with while solving the Schrodinger equation for the hydrogen atom. Out of this, we are already familiar with the L and M because we saw the equations that we obtained in the case of a hydrogen atom. Certain equation, for example, specifically saying the F equation and the P equation in the case of hydrogen atom was exactly similar to the corresponding equations that we learned in the case of particle on a sphere. Okay, for example, if you are considering a particle on a sphere case and hydrogen-like atom case, we saw that we have the equations like F equation in the case of sphere. Okay, F equation in the case of sphere was f of I is equal to 1 divided by root of 2 pi e raised to I m phi. Okay, and we have the similar equation here also in the case of hydrogen like atom, that is f of I is equal to 1 divided by root 2 pi e raised to I m phi. Okay, we have the same equation in both cases, and here we have a number, that is m, and this nature of this m was already established in the case of the particle on a sphere. I am not going to repeat this because we already discussed this in detail, and there we found that m can have the values 0, then plus or minus 1, plus or minus 2, plus or minus 3, etc. Okay, and here also we reached the same equation containing m. Therefore, the whatever considerations we put there in the case of the particle on a sphere, the same considerations can be put here as well, and we can establish that m in this case is also equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. These are the possible values of m in both cases. Then we found another equation, that was P equation, right? P equation, P equation, P equation, and the P equation in the case of the particle on a sphere, and this equation was d square P by d theta square, right? D theta square plus cos theta by sin theta dp by d theta plus beta p is equal to 0. This was the P equation we obtained in the case of particle on a sphere. And the same equation we got in the case of hydrogen like atom also. That is d square p. We can see this equation. We already solved this equation, right? D square p by d theta square plus cos theta by sin theta dp by d theta plus beta p is equal to 0. So in both cases we got this equation, and here in this equation beta in both cases, beta is nothing but L into L plus 1. So this equation contains a new number, that is L, and this nature of L was established in the case of particle on a sphere. You may be remembering that we established that the nature of L is like L is equal to 0, 0, 1, 2, 3, etc. These are the possible values of L. So the same considerations can be put here in the case of hydrogen like atom also. And we can establish that L in this case is also equal to L is equal to 0, 1, 2, 3, etc. Okay. So these two equations, the F equation and the P equation, we got similar equations in both cases, that is the particle on a sphere and hydrogen atom. And in these equations we found, or we encountered, two numbers, that is L and M. And we established the nature of L and M in the case of particle on a sphere. The same thing can be established here in the case of hydrogen-like atom also. So we already know the nature of M and L. Okay, M and L. And now there is a relation between L and M that also we established in the case of particle on a sphere. And there we established that the value of M depends upon L. For a given value of L, for a given value of L, what are the possible values of M? M is equal to minus L, then minus of L minus 1, etc. through 0 to plus L minus 1, then last value is plus L. So the possible values of L are minus L to plus L through 0. Okay. So left side to the 0 there are L values. Right side to the 0 there are L values, and including 0 2L plus 1 values, right? There are 2L plus 1, 2L plus 1 M values are there, M values corresponding to a given value of L. Okay. And this we established already in the case of particle on a sphere. The same applies here in the case of hydrogen atom also. Now, in the case of the hydrogen atom, we had an additional equation. That equation was not there in the case of particle on a sphere. This was R equation. Okay, R equation. And this R equation was absent in the case of particle on a sphere because we saw that we consider a particle which is moving on the surface of a sphere. The surface of the sphere has a constant value for its radius, right? Whenever when the particle is anywhere on the surface of the sphere, in all these cases R is constant, or the radius of the sphere is constant. So R is not a variable there. So we had no equation containing the variable R there. But here in the case of hydrogen-like atom, R is not a constant. Here R is a variable. Okay. Therefore, we had an equation in terms of R, that was R equation. We modified this R equation many times for the purpose of solving it. And I am writing the modified R equation, that is d square R divided by d rho, d square R by d rho, plus 2 by rho dr by d rho plus minus 1 by 4 plus n divided by rho plus minus L into L plus 1 divided by rho square, right, into R is equal to 0. This was one of the modified R equations, right? And here rho is 2Zr divided by Na0. So rho is depending on R, right? And we found what is the solution of this equation. And from here we solved for R, and the solution of this equation is RNLR is equal to, that is rho raised to L n plus L 2L plus 1 rho, then exponential minus rho by 2. Okay, this was the solution of this equation, where rho is equal to 2Zr by Na0. And here we had a polynomial, that is L n plus L 2L plus 1 rho, L n plus L 2L plus 1 rho. Okay, this polynomial is the associated logarithm polynomial. We already learned this, right? associated Laguerre polynomial. Laguerre polynomial. Associated Laguerre polynomial. And the associated Laguerre polynomial, we already learned the nature of the associated Laguerre polynomial. LKPX. And in our case, in place of k, we have n plus l, and in the place of p, we have 2l plus 1. Okay. So the associated Laguerre polynomial LKPX. In this case, we already proved that p must be less than or equal to k. That we have already proven, right? P must be less than or equal to k. We took many examples to prove this. And if you don't know this, please watch my previous lectures. There I have shown why it should be p less than or equal to k. Okay. If p is greater than k, then the polynomial will vanish. Okay. The polynomial will vanish. But we have already established this fact. So in our case, in place of LKPX, we have Ln plus L, 2L plus 1 rho. Okay. This is our polynomial. So P must be less than or equal to K. So in our case, we can write P is 2L plus 1. 2L plus 1 must be less than or equal to K. K in our case is N plus L, right? Or we can write, we can cancel one L from each side. Then we have L plus 1 less than or equal to N, or we can write L less than or equal to N minus 1, right? So L is less than or equal to N minus 1. What is the meaning of that? The L can have a value equal to N minus 1, or its value should be less than N minus 1. It means the maximum value of L. Maximum value of L is equal to N minus 1. Okay. N minus 1 ആണ് L ന്റെ maximum value. Minimum value നമ്മൾ already established ചെയ്തിട്ടുണ്ട്. We already established that the minimum value of L is equal to 0, 1, 2, 3. L is equal to 0, 1, 2, 3, etc. What is the minimum value here? 0. So L is equal to 0. That is the minimum value of L. So the minimum value of L is equal to 0. So which are the possible values of L then? So L is equal to 0 to N minus 1. Okay, these are the possible values of L. 0 to N minus 1. And we don't know anything about N here, right? What is the nature of N? But it is very easy to establish now the nature of N. Okay. You know that L can have the values 0 to N minus 1, right? And in order to make it more clear, I am going to consider the degree of the polynomial. We have already learned what is meant by the degree of the polynomial. Degree of the polynomial LKPX is equal to K minus P. That is the degree of the polynomial, right? Degree of the polynomial. So degree of the polynomial is equal to K minus P. This is the degree. And in our case, K minus P is, what is K minus P in our case? In our case, K is equal to N plus L. P is equal to 2L plus 1. So in our case, K minus P is equal to N plus L minus 2L plus 1, right? N minus 1 minus 2L plus 1. So what is it? N plus L minus 2L minus 1. So that is equal to N minus 2L, that is minus L minus 1. So the degree of the polynomial is N minus L minus 1. And this degree of the polynomial, we have already established in the previous video that the degree of the polynomial will be 0, 1, 2, 3, etc. These are the possible values of the degree of the polynomial. So N minus L minus 1 is equal to 0. Okay. Another possible value of the degree of polynomial is 1, then 2, then 3, etc. Right? These are the possible values of the degree of the polynomial. The degree of the polynomial cannot be like 0.5 or 1.7, etc. These are the degrees of the polynomial. Okay? Associated log array polynomial. And when L is equal to 0, we already know that from this equation, we can say that this is a n minus L minus 1, right? Therefore, from this one, n is equal to, what are the possible values of n from this one? In this case, when n minus L minus 1 is equal to 0, in this case, n is equal to L plus 1, right? L plus 1. When n minus L minus 1 is equal to 1, then in that case, n is equal to, when it is equal to 1, n is equal to L plus 2, L plus 2. And when n minus L minus 1 is equal to 2, then you can say that n is equal to L plus 3. And in this case, it is L plus 4, etc. So these are the possible values of n. N value should be L plus 1, L plus 2, L plus 3, L plus 4, etc. Okay? Where L can have any value, any allowed value. Which are the allowed values of L? The allowed values of L is equal to 0, 1, 2, 3, etc. So the minimum value of L will be obtained when the minimum value of n is obtained when L can have its minimum value. What is the minimum value of L? 0. So when L can have the minimum value, we can substitute the minimum value of L in these equations. So what will be the minimum value of n? The minimum n is equal to the minimum value of L, that is 0 plus 1, that is equal to 1. In this case, if we are substituting the minimum value of L, it is 0 plus 2, that is equal to 2. Okay, so this will be 2, and this will be 0 plus 3, then 0 plus 4, 4, etc. So these are the minimum values of, this is the minimum value of n. And if you are substituting any value of n, for example, if you are substituting the next higher value of n, then you will have the values like 1 plus 1, that is 1 plus 1 is equal to 2, then 1 plus 2 is equal to 3, then 1 plus 3 is equal to 4, 5, etc. If you are going for the next higher value of L, that is 2, then 2 plus 1 is equal to 3, then 4, then 5, etc. Here in all these cases, you can see that n can have the values. The minimum value of n is equal to 1, and the other allowed values are 2, 3, 4, 5, etc. Right? So this establishes that the n must be an integer. Since L is an integer, n must be an integer, and the minimum value of n is equal to 1. So let us say that the values of n is equal to 1, 2, 3, etc. And now what is the relation between the value of n and L? We already established here that L should be less than or equal to n minus 1, or L should be equal to 0 to n minus 1, where n is any integer starting from 1, right? So this means that for n is equal to 1, L is equal to 0 to n minus 1, that is 0 to 1 minus 1, that is 0. 0 to 0 means 0 only. And the possible values of m is equal to minus L to plus L, that is minus 0 to plus 0, that is equal to 0 itself. So this is a possible set when n is equal to 1. And when n is equal to 2, L is equal to 0, 1, that is 0 to n minus 1. And m is equal to, m value depends upon the L value. When L is equal to 0, the m value is equal to 0. When L is equal to 1, then the m values is equal to minus 1, 0, plus 1. Write that, right? So now you know how to establish the value of n, L, and m. Now we have seen that n It is very important to note here that n is equal to 1, 2, 3, etc. It means that the value of n is restricted. It can have the values, the all integer values like 1, 2, 3, etc. Okay. It cannot have a value like 1.5. It cannot have a value like 2.8 or 3.3, etc. These are not allowed. Its values are restricted like 1, 2, 3, etc. Okay. And here we have to remember that we introduced the n. You remember when we introduced the n, right? We introduced the n as a natural constant. For example, when we were solving the R equation, we put n square is equal to minus 2 pi square m z square e raised to 4 divided by 4 pi epsilon 0 square h square e. So these constants appeared in our equation, and all these together was called as n square. So n square, or in other words n occurred naturally, right? N occurred naturally. At that point of time, we didn't know whether n is a quantum number or not. You may be remembering what I said at that time. We don't know whether n is a quantum number or not. We didn't know at that time. When we introduced the new constant n, at that point we didn't know whether the value of n is a quantum number or not, because we had it's something like e, and we had no clue about the nature of e, and therefore I said that we don't know whether n is a quantum number or not. But at this moment we know that n is a quantum number because it has restricted values like 1, 2, 3, etc. Okay. So now we have a new quantum number n, and this new quantum number n is called the principal quantum number. Okay. So this is what you have to understand about the nature of n, l, and m. Perhaps now you may be very happy that in your previous classes, okay, for up to your final year BSc classes, you learned these quantum numbers n, l, and m when you learned the atomic structure. Okay, at that time you just memorize, you just by heart that this is a quantum number and it can have only certain restrict values. At that time you were not knowing why these are quantum numbers and why it has only restricted values. Okay, at that time you didn't know that, but at this moment you know why it is called a quantum number and why it has only a restricted value. There are some mathematical limitations for these numbers to get any value, right? So these are quantum numbers. Okay, so now we have established the three quantum numbers in the case of while deriving the Schrodinger wave equation for the hydrogen atom. Still, there is another quantum number, that is the spin quantum, that we will learn in another occasion. But at this moment, these are the three quantum numbers that we are establishing while solving the Schrodinger wave equation for the hydrogen atom. Okay, and this leads to a new model of atom. Okay, I will talk about the nature of these in detail in another occasion, and this leads to a new model of atom, that is quantum mechanical model of atom, and we will go to the details of that in the coming videos. Okay, and thank you for watching and stay tuned.